Excuse me. Chemistry 3101, Organic Chemistry 1. This is Chapter 4, where we deal with alkanes and cycloalkanes. So we're talking about compounds that are hydrocarbons. And hydrocarbons are compounds that contain only hydrogen and carbon. And you'll see that alkanes and cycloalkanes only contain two elements, just hydrogen and carbon. So alkanes and cycloalkanes belong to a class of carbons that we refer to as hydrocarbons. So hydrocarbons are any type of compound that is composed of only hydrogen and carbon. Again, in this chapter, in this chapter, we're going to focus on alkanes and cycloalkanes. But besides ethane, which is an alkane that you see here, so besides alkanes, also falling under the umbrella of hydrocarbons would be alkenes. So an alkene would fall under that umbrella, an alkyne, and also aromatics would fall under there as well. And you can see that we have some specific compounds here. We have ethane, ethylene, acetylene, and benzene. I'll just throw one bug in your ear. We're not going to talk about alkyne nomenclature for a while, but acetylene is a common name. The IUPAC name or systematic name for this molecule is actually ethine. So I'm just going to put that here in brackets, ethine. So you can see how there's kind of a trend going from ethane to ethylene to ethine. Anyhow, and then we've got benzene. And we can classify hydrocarbons as being either saturated. We can have saturated hydrocarbons like an alkane, or we can have unsaturated. And alkenes, alkynes, and aromatics would all fall under the umbrella of being unsaturated hydrocarbons. What does that mean? It means that they do not have the maximum number of hydrogen atoms per carbon. If you look at ethane, you see that we have two carbons, and the maximum number of hydrogens that you can have when you've got two carbons is 6. You cannot have any more than 6. There's no such thing as C2H7 and beyond. It doesn't exist. But if you have two carbons and you have less than 6 hydrogens, for example, if you have 4 or 2 hydrogens, then you don't have the maximum number, and so we say it's unsaturated, an unsaturated hydrocarbon. Another way to recognize an unsaturated hydrocarbon is any hydrocarbon that's got a pi bond in it. So we have 1 pi bond here, we have 2 pi bonds in the alkyne. A pi bond represents unsaturation. If you take a look at benzene, why is it unsaturated? Well, you can see that it's got 3 pi bonds in it, so therefore it has to be unsaturated. Another way to know that something is unsaturated is if it has a ring. So we'll put here unsaturated, could have a pi bond or a ring. In benzene, you've got pi bonds and you've also got a ring. So you've got 4 what we call units of unsaturation. If you're wondering, is there a formula that I can use to predict the maximum number of hydrogens that I could have in a carbon? The answer is yes, there is a formula. The formula that we use for saturated hydrocarbons is CnH2n plus 2. So you see that we have 2 carbons here. So we have C where N is 2. If you take H and you take 2 times 2 plus 2, 2 times 2 is 4. 4 plus 2 is 6, so you get C2H6. You could do that again for any hydrocarbon. Let's imagine you had 10 carbons. What would be the maximum number of hydrogens you could have? C10H2n plus 2. H2 times 10 plus 2. 2 times 10 is 20. 20 plus 2 is 22, so that would be C10H22 would be the maximum number of hydrogens you could have in a saturated hydrocarbon with 10 carbons in it. Well, where do we come up? How do we name alkanes? If you go back to your general chemistry days, you learned how to name all the polyatomic ions like sulfate, sulfite, nitrate, chromate, dichromate. You learned how to name molecular compounds like carbon dioxide, dinitrogen monoxide. What else? You learned how to name ionic compounds like sodium sulfate and ammonium carbonate, all those good kinds of things. But now we're going to talk about how do we name an alkane. And it says here that many organic compounds have common names. In fact, when scientists first started isolating and determining the structures of organic compounds, they just gave them any old random name, names that they liked. for example, formic acid, you see formic acid here, that was isolated from ants and named after the Latin word for ant, which is formica. Urea, I think it's pretty easy to guess where that one comes from. Urea was isolated from urine, but another one that's kind of interesting is morphine. If you're wondering where the word morphine comes from, morphine is named after Morpheus, who was the Greek god of dreams. And another one that you might find amusing is barbituric acid was isolated by Adolf von Baer, the same Baer who started the Baer, pharmaceutical company, which is still around today. He just named it after some woman named Barbara that he was infatuated with. So, all kinds of interesting historical names out there. However, we don't really use that anymore. Yes, for marketed drugs, they'll have, trade names like Zoloft and Losec and that kind of thing, Lipitor. However, drugs will have they'll have IUPAC names as well. And so we have to learn how to name alkanes according to the IUPAC rules. And if you're wondering what IUPAC is the International Union of Pure and Applied Chemistry. The same rules that you would have used in general chemistry to name ionic and covalent compounds, we use a systematic way of naming organic compounds like alkanes. Why do we do that? So that scientists all over the world can communicate with one another. Well, again, for you to be able to name alkanes, you have to have mastered bond line structures, right? You've got to be able to look at this structure here and understand how many carbons are in here and how many hydrogens are bonded to each carbon. So if you need to review that, go back to chapter 2 in my lecture slides, or you can go back to chapter 1 and chapter 2 in the textbook where it discusses bond line structures. But here we go. How do we name an alkane? The first thing that we do is we identify the parent chain. What's the parent chain? The parent chain is the longest consecutive chain of carbons. You can see that I have it highlighted in red, and that chain contains 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. How do you find the longest carbon chain? Well, you find it by T&E, trial and error. You might have looked at this molecule and said, well, I think the longest carbon chain, I think it goes like this. I think it goes 1, 2, 3, 4, 5, 6, 7, 8. That's pretty long. There we go. That's the longest carbon chain. No, you have to keep trying until you find it. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. Let's keep working at it. Let's see here. What if we tried, 1, 2, 3, 4, 5, 6, 7. No, it's not that. And then you keep looking and you end up finding that it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be the parent chain, what I have highlighted in red, the longest consecutive chain of carbons. How do you name that longest carbon chain, that parent chain? Well, we name them according to the number of carbons that are in that chain. If you have 1 carbon in the chain, we call that methane. If you have 2 carbons in the chain, we call that ethane. If you have 3 carbons in the chain, we call that propane. If you have 4 carbons in the chain, we call that butane. 5 is pentane. 6 is hexane. 7 is heptane. 8 is octane. 9 is nonane. And 10 is decane. I ask my students to memorize the first 10 hydrocarbons, straight chain hydrocarbons. So we'll put here, memorize those ones. If you want to try to memorize the rest of what's in this table, it is not required. You do not have to memorize any of these in here. However, they are kind of useful. Take a look. If you have 11 carbons, we call it undecane. 12 is dodecane. 13 is tridecane. 14 is tetradecane. 15 is pentadecane. If you have 20, you have an icosane. And that's kind of interesting because in biochemistry, sometimes they talk about what are called icosanoids, like prostaglandins and thromboxanes and leukotrienes. Anyhow, that's neither here nor there. Then 30 is a tricontane. What else? You've got 40 is a tetracontane, 50 is a pentacontane, and then 100 is a hectane. So now you can say, what in the hectane? When you're talking to a friend studying organic chemistry. But we'll put here, not required. Okay, so we'll write down here for these ones, not required. But memorization. Memorization. memorization not required for those ones. Just the first 10. And when we're talking about straight chain alkanes, that means just one carbon after another, like 1, 2, 3, 4, 5, 6, 7, 8, like that. Sometimes we call these N-alkanes. You might see that on the internet if you like to peruse the internet. N-alkanes, the N stands for normal alkanes. So normal alkanes, that's what the N stands for. And N-alkanes, N for normal. It's kind of funny. But all that it means is that they're straight chains. Okay. So we'll put here straight chains. And if you're wondering, well, what's not a straight chain, Mr. Dion? Well, we're going to get into that in a few minutes. We're going to talk about branching. Well, I told you that we're going to talk about alkanes, and so far we've looked at alkanes that are, not having any rings in them except for benzene. But what if you do have a ring? Well, if you have the parent chain and it's in a ring, okay, it's all held together in a ring, then we use the prefix cyclo. So here we have 3 carbons in a ring. So we would call this cyclopropane, right? We have a CH2 here, CH2 here, CH2 here. So that's cyclopropane. Then if you have 4 carbons in a ring, we call that cyclobutane. When you have 5, we call it cyclopentane. What do you think it's called if you have 6 carbons in a ring? Could anybody guess based off of the table? Yeah, 6 carbons, what would you call that? Yeah, absolutely, Tracy. It's cyclohexane. So cyclohexane. And then if you have 7 carbons in a ring, like this, that would be, that's not a very good drawing, is it? There we go. This would be cycloheptane. If you're wondering, can you have cyclooctane? Of course, right? It's shaped like a stop sign. An octagon. So if you have 8 carbons in a ring, that would be cyclooctane. And you can have cyclononane and cyclodecane or whatever. But anyhow, these are the rings that we're going to focus on. In fact, we're going to spend a lot of lecture time on Thursday talking about cyclohexane. And I'm going to explain why we spend so much time talking about cyclohexane. All right, so there you go, some cycloalkanes. And then what if you have something coming off of your parent chain? What do you call that? Well, we call those substituents, first of all. And if they're straight, meaning that they're just going, like this, like 1, 2 carbons, or 1, 2, 3, or 1, and there's no branching off of the substituents, we name them as alkyl groups. So if you have just 1 carbon, we call that a methyl, right? If you just have CH3, right, like this here would just be, this would be a methyl group because there's just a CH3 there. Again, this is a bond line structure. It's implied that there is a CH3 off of here. If you have a CH2, CH3, so you take ethane and you knock a hydrogen off of it, we call that an ethyl group. So if you look over here, you have a CH2 and a CH3. And so this here would be an ethyl group. If you have 3 carbons, so CH2, CH2, CH3, then you call that a propyl group. And you can see that that's what we have here. We have CH2, CH2, and another CH3 here. So this would be a propyl group. And of course, if they're longer, if you have 4 carbons, then it's a butyl, a pentyl, a hexyl, a heptyl, an octyl, a nonyl, a decyl. So we'll just scribble in here. A butyl group would be CH2, 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 CH3, like that. But again, we like to use bond line structures rather than writing out condensed structures because they're so much faster. All right. So those are the first substituents you need to learn. Methyl, ethyl, propyl, butyl. Beyond these, like the pentyl, hexyl, heptyl, octyl, nonyl, decyl, these could show up. We don't see them nearly as much as the first 4. We usually see the first 4 alkyl groups coming up all the time. And what's interesting is that once you get to propyl and butyl, you have more than one way to arrange the carbon atoms that are in these alkyl groups. And I'm going to show you that in just a second. So let's go to rule number 2, and it says identify and name the substituents. So a ring can either be a parent chain or a substituent depending on how many carbons it has in it. If the ring has more carbons than the substituent, then it becomes the parent, or it is the parent. So if we were to number this compound, you see that we have 1, 2, 3, 4, 5, 6 carbons in the parent, and we have 1, 2, 3 carbons in the substituent. So you would call this propyl cyclohexane. First you list the substituent, and then you list the parent. The parent always comes last. And there's sometimes I'll get a student saying, well, isn't there more than 6 carbons? Couldn't you do 1, 2, 3, 4, 5, 6, 7, 8, 9? The answer is no, you cannot do that, because you'd have to go back. You'd go from here, and then you go through this carbon again. You cannot pass over a carbon twice. It cannot be done. And so the way that I had it originally is the correct way of doing it. So the parent in this case happens to be the ring, but if you look at this example, the parent is not the ring, because the chain here has 1, 2, 3, 4 carbons in it, and the ring only has 1, 2, 3. So the ring is smaller than the chain. And so we list the substituent first, which in this case is a ring, which is a cyclopropyl. So this is our substituent. And then butane happens to be our parent, because butane has 4 carbons in it. All right. And if you're wondering, why do you have a 1 in front of this one? Well, it's because the cyclobutyl group, the cyclopropyl group, is attached to carbon number 1. If you're wondering, well, why do I have to put that in there? Well, imagine if you had 1, 2, 3, 4 carbons like this. So this is a butane, 4 carbons. But imagine you had the cyclopropyl coming off of here. In that case, you would number these as 1, 2, 3, 4. And the substituent is at carbon number 2. And so this would be 2 cyclopropyl butane. We're going to talk more about these numbering things in a few minutes. Now, if you have what's called a complex branch, which is, branches that are just, complicated, okay, well, first of all, there's not even that many practice problems in the textbook that even cover this. However, the way that you name complex branches is you start with the longest chain within that substituent. You're going to start with the carbon attached to the parent. So this is our parent chain right here. So this is the parent. That means that everything in green is the substituent. And we start with this carbon, the one that's attached to the parent. We have 1, 2, 3, 4 carbons. So that's a butyl group, the longest chain. But then you have a methyl group up here, a CH3. So you would call this 2-methyl-butyl, and you put brackets around it. Okay, so you have brackets around the complex substituent. Again, this is one of those things that really crystallizes in your mind when you get a chance to practice it. So we'll do some practice in a little bit. I want to go back to this whole idea of alkyl groups. And I told you that when you have a methyl and an ethyl, there's no way to reorganize or to rearrange the carbons in a methyl or ethyl group. There's nothing you can do. However, if you look at the formula for a propyl group, the formula for a propyl group is C3H7, and the formula for a butyl group is C4H9. So these are the formulas for the propyl group and the butyl group. The thing is, if you have 3 carbons and 7 hydrogens, there's a second way that you can organize these atoms. So we'll put here plus, use my blue pen, put +1. And then with a butyl, when you've got 4 carbons and 9 hydrogens, then there's even more possibilities. You can arrange them in this manner, and there's also 3 other ways that you can do it. Let me show you how you can reorganize those atoms to make even different alkyl substituents. We'll start with the propyl. Again, the propyl was C3H7. The first way that we had was CH2, CH2, CH3. That's what we call a propyl. However, you can also have what's called an isopropyl. You see the complex way of naming it is down here, 1-methyl ethyl. We'll almost never ever use that. We're always going to use isopropyl. And you can see how you have CH here, a CH3 here, and a CH3 here. Tally up the carbons. You can see that we have 1, 2, 3 carbons. We have 3, 4, 5, 6, 7 hydrogens, C3H7. They're just rearranged in a different manner. So an isopropyl is just an isomer of a propyl substituent. So we have the propyl and the isopropyl. Give me a thumbs up if you follow me on the propyl and the isopropyl. Is everybody with me on that? Because we're gonna move on to the butyl. That's a lot of thumbs. Good, because butyl gets, butyl. Maybe that could stand for, you could call it brutal. I don't know. There's 4 different isomers for a butyl. Let's go back here. Okay, with C4H9, you have not only this, but you have 3 other ways, and you have to memorize all of them. So let's go down here, and I'll show you the sec-butyl, isobutyl, and tert-butyl. So here we are. Again, all of these are C4H9. We have the butyl, which is CH2, 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 and CH3. Then we have the sec-butyl, where we have a CH, a CH3 here, a CH2 here, and a CH3 here. In the isobutyl, the way that you can compare it to the isopropyl is the isopropyl ends up with 2 CH3s on the end, like this, and so does the isobutyl. So we have a CH here and a CH2 here. And then for the tert-butyl, you have a carbon with no hydrogens attached to it, and then you have 3 CH3s. 1, 2, 3. And again, all of those have the same formula. All of these alkyl groups are C4H9, but you have to memorize the butyl, sec-butyl, isobutyl, and tert-butyl. These come up all the time in organic chemistry. If you're wondering, do we have common names for the substituents when we have 5 carbons? The answer is yes. There's pentyl and isopentyl and neopentyl. However, we are not going to use any of those in this class, so do not worry about them. If you find them on the internet or something, don't worry about them. Again, we're not going to cover them in this class. So what are the groups you need to know? Let's go back. You need to know methyl, ethyl. So you need to know the methyl group, the ethyl group. You need to know the propyl group. You need to know the isopropyl group. And then for the butyl groups, you need to know butyl. You need to know isobutyl. You need to know sec-butyl, and sec-butyl has a hyphen in it. And then you need to know tert-butyl, and tert also has a hyphen in it. Butyl. Let's highlight those hyphens so you know that there's 2 of these that are hyphenated, the sec-butyl and the tert-butyl. And the hyphens are going to be important, believe it or not. They're actually important when you get into the names. There you go. So let's put a box around these, and we'll call this alkyl groups to memorize. And, initially it's going to be memorization, but once you get enough practice with it, it's going to be in your head, and it's going to be good forever. You're always going to use the same alkyl groups in organic chemistry. Let me just encourage you, if you're just thinking, oh man, another thing to memorize, I had to learn those pKa values, functional groups, and now this, Mr. Dion. Well, if you think about it, you're learning the subject. You're just starting out in, starting out in any subject is kind of like learning a language, where you have to learn all the rules and things before you can really start getting into, organic reactions. So we're still kind of learning the ropes here, so to speak. But one great thing about being a scientist, you guys, or especially an organic chemist, is that all these alkyl groups that you memorized, they're going to be the same next semester. They're going to be the same next year. They're going to be the same 10 years from now. They're going to be the same 50 years from now. So the names of the alkyl groups are not going to change. Once you have them memorized, you're done. Okay? Whenever you see them again for the rest of your life, you are good. The same thing with the memorizing the first 10 hydrocarbons. Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. Once you have those in your brain, they're good forever. Forever, it's never going to change. So that's a great thing. If you study computer science, God only knows, the textbook is probably good for, what, a month or something, and then you have to throw it away. I don't know, I'm being silly. But you get my drift. All right. So how do we assemble these IUPAC names? Well, you can imagine there's some guidelines, and I don't like to generalize. However, one thing I've kind of noticed, and I've told you this before, one thing I've noticed as a chemistry teacher and just a scientist in general is that science students, and myself included, we kind of like rules. We're like, give me the rules, Mr. Dion. I'm going to follow those rules, and then I'm going to get a good grade. And I don't think there's anything wrong with that approach. So let me just introduce you to the rules of assembling an IUPAC name. Rule number 1, if you have only one substituent on your parent chain, you number the parent chain so that you end up giving the substituent the lowest possible number. You can see that I have a heptane here. This is a heptane, okay? And this is a heptane as well, because the longest carbon chain has 7 carbons. However, we start numbering on the left. Why? Because we have a methyl group here, and you want to give that methyl group the lowest number possible. Well, 2 is lower than a 6, and so, again, we start numbering on the left. So we have 2-methyl heptane. So we could put that down as the name. This would be 2-methyl heptane. Anyhow, and if you're wondering, why do you have a hyphen in here? Why is it 2 hyphen? Well, let me just tell you quickly. Whenever you have a number and a letter in a name, so number, let's write it down up here. If you have a number and a letter in a name, you always separate them with a hyphen. And if you have a number and another number, you separate them with a comma. That's a pretty ugly comma. Let me fix that. So here we go. Number and number are separated by a comma. So hyphen between any number and letter, and a comma between any 2 numbers. Otherwise, you just put all the letters together. Okay, let's move on to the next rule. When you have multiple substituents, you number the parent chain, and you give the first substituent the lowest possible number. So you look at all the different substituents on your parent chain. You can see that both of these are heptanes. We have 3 methyl groups. We've got 1 here, we got 2 here. Well, how would you number it? The way that's on the left or the way that's on the right? You're going to number it starting with carbon number 1 being the one on the left. Why? Because then you have a 2-methyl. If you were to start numbering over here, then you have a 3-methyl. You've actually got 2 of them. You call that a 3,3 dimethyl. So if you look at the numbers that you give for the substituents, here you have 2, 5, and 5, whereas over here you'd have 3, 3, and 6. Well, you go for the first point of difference, and 2 beats a 3. 2 is lower than a 3. Look deep into my eyes. No, you can't see me. But anyhow, I was going to try to hypnotize you maybe. You don't have to do any kind of mathematics. 2 plus 5 plus 5 and 3 plus 3 plus 6. It's got nothing to do with any algebra. The answer is you give the first substituent the lowest number possible, and that's it. Don't worry about the rest of the substituents. Just the first substituent on the parent chain gets the lowest possible number. Next. What's next? It says if there is a tie, then you keep looking for something that's going to break that tie. Well, check these 2 molecules out. You can see that over here on the left, we've got a methyl at carbon 2 and 6. Over here, we've got a methyl at carbon 2 or 6. Whether you start numbering from the left or start numbering from the right, so you look for a point of difference. If you look at the way that they're numbered on the left, you have a methyl group at carbon 3, whereas over here, you've got one at carbon number 5. So what are the numbers? On the left, we have a 2, a 3, and a 6. On the right, we have a 2, a 5, and a 6. Well, we look for the first point of difference, and the first point of difference is what's highlighted in green or circled in blue, and a 3 is lower than a 5. Therefore, this is the correct way of numbering, and this would be incorrect. So look for the first point of difference. You might be wondering, well, what if there's no point of difference, Mr. Dion? Well, what if there's no point of difference, and you've got 2 different substituents, like a chlorine and a bromine? Well, in that case, you go with alphabetical order, A to Z, okay? So you see that in both of these molecules, we have a chlorine and a bromine on the end. I didn't cover the prefixes or the naming for halogens as substituents, but if you have a fluorine, you call that a fluoro. If you have a chlorine, that's a chloro, as you can see on here. If you have a bromine, that's a bromo. And I bet you can guess what an iodine is called. It's called an iodo. Okay, and if you're wondering why are halogens so dang important in organic chemistry, you've brought them up a bunch of times. The reason why is because when we get into things like chapter 7, if you've ever heard of SN2 and SN1 reactions, if you've read the entire book already, maybe you have. Hopefully you haven't, but anyhow, if you did, you get to realize why halogens are so important in organic chemistry. But you know what? That's for another day. So let's not worry about that. Let's just worry about naming them right now. So we go for a tiebreaker. And in this case, we go alphabetical order. Well, B beats C. B comes before C in the alphabet. You can sing the song if you want to. And so one bromo is going to beat out one chloro. All right. So there we go. And then all the same rules apply for cycloalkanes. You can see that the parent chain in this molecule has 6 carbons, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. But the reason why the numbering on the right is incorrect is because sure, you have a substituent at the first carbon, but then you've got 2 substituents at carbon 3. So the numbers would be 1, 3, and 3. Whereas on the left, it's correct because you have 1, 1, and 3, and you look for the first point of difference. A 1 beats a 3 that we have highlighted in green here. There we go. And this is how we assemble all the names. It says put the number and the name of each substituent before the parent. We put them in alphabetical order. If you have the same alkyl group or halogen showing up more than once, we use prefixes. We use di if it shows up twice. We use tri if it shows up 3 times. We use tetra if it shows up 4 times. We use 5 if it shows up, or penta if it shows up 5 times. And you ignore those prefixes. So let's say you have a dimethyl. So let's say you have dimethyl. You ignore the prefix di, and you would alphabetize according to the letter N. Let's say you had, I don't know, tetraethyl. You had 4 ethyl groups. You would alphabetize according to the letter E. There are some exceptions for substituents. It says here iso. There's more substituents than that. The substituents where you alphabetize according to the prefix would be iso, cyclo, and neo. We won't even see neo in this class, but it might show up, the word might show up, or the prefix might show up somewhere. And so let's say you had, what did we look at before? We looked at isopropyl. So isopropyl, propyl is an exception. So you would alphabetize according to the letter I. What else? If you had, cyclo, let's say you had cyclobutyl, you would alphabetize according to the letter C. So to summarize, we identify the parent chain, we identify and name the substituents, we number the parent chain, we give a locant. A locant is nothing more than a number, each substituent, and then we list the numbered substituents before the parent name in alphabetical order. And those are all the rules for nomenclature. Let's go back and look at some of these compounds now that we know the rules. Let's go to the way back here. So where were we? Somewhere around here. So we had named this compound 2-methylheptane. So we got that one down. But we didn't name this compound here. Here you've got a 2-methyl, then you've got 5 and 5-methyl. All of those are identical. And so you would call this 2-5-5 trimethyl heptane, because the longest carbon chain or the parent contains 7 carbons. So that would be this compound. We go to this one here. We have methyl groups at carbons 2, 3, and 6. So you'd call this 2, 3, 6 trimethyl heptane. So that's the name for this compound. If we look at this compound, well, 1 bromo beats a 1 chloro. So you'd call this compound 1 Bromo. Remember, letters and numbers are separated by hyphens. So that's our bromo, B for bromo. Then you have to list the next substituent, which is the chloro. 5-chloro. And then the carbon chain contains 5 carbons, so this is some kind of pentane. Right, so that's this one. And then let's put the right name for this one. Could I give you a second to try to name this compound? I'll give you a second. If anybody can come up with a name, you can either unmute your mic or type it in the chat. We can take a looky at it. (1,1,3) trimethyl. Yes, I think that's beautiful. Keanu, that looks great to me. Yeah. You've got 3 methyl groups, so we have trimethyl, and the locants or numbers would be 1, 1, 3, trimethyl cyclohexane. Remember the numbers? We call these locants. Locants is what those are called. There we go. Beautiful. Perfect. Give me a thumbs up if you follow me on the rules. Are there any questions about the rules? You might have questions as you try, practice problems, and that's totally normal. Okay, I wouldn't expect you to not have questions. However, how are you going to master nomenclature? The only way to master it is to practice it. Let's take a look at a problem here. Now we're going to try something a little juicier, a little more complex. It says we want to name this compound. We see the longest carbon chain contains 1, 2, 3, 4, 5, 6 carbons. And we want to number it in such a way that we give the locants the lowest possible number. So we're going to start here with 1, 2, 3, 4. So that way we have 2 substituents here, 1 at 3 and 1 at 4. Our locants, our numbers would be 1, 1, 3, and 4. You might have thought, well, why don't I start up here? 1, 2, 3, 4, because then your numbers would be 1, 2, and 4, 4. This is the point of difference. And so the numbering in red is correct and the numbering in blue is incorrect. Sometimes I like to make a little laundry list. I call this, I don't know why I call it that. I just call this my list of substituents. So I'll write down what I've got. I've got a tert-butyl at carbon 4. I've got an ethyl at carbon 3. I've got 2 methyls at carbon 1, so that makes a 1,1 dimethyl. I know my parent is cyclohexane, and I'm going to alphabetize my substituents. Remember, you ignore the prefix tert. You've got the B for butyl. You've got E for ethyl, and then you ignore the D for dimethyl. You alphabetize according to the M. So we're going to list the tert-butyl, then the ethyl, then the dimethyl, and then we put it all together in a big, tasty nomenclature sandwich. And we have 4 tert-butyl, 3 ethyl, 1, 1 dimethyl cyclohexane. Nothing more to it than that. Okay. Let's try one where we have a side chain or a substituent that is something common. It says provide systematic names for each of the following compounds. Let's see here. In B, who could tell me how many carbons are in the longest carbon chain here? There's no tricks. Mr. Dion does not like tricks. Yes, absolutely. 6 carbons, right? The cyclohexane is the longest carbon chain. So we'll scribble that down. We've got 1, 2, 3, 4, 5, 6. I went counterclockwise. It wouldn't matter if you went clockwise. You get the same answer no matter what. I got one for you, and this isn't easy. But there's a total of, where's my red pen? There's a total of 1, 2, 3, 4 carbons in this side chain. Could anybody tell me, is this a butyl, tert-butyl, isobutyl, or sec-butyl? Could anybody tell me which one? And you might have to go back. It's not the tert-butyl. Yes, it's the sec-butyl. That's right. So this is a sec-butyl. All right. So we have the sec-butyl. So it might be a knee-jerk reaction to say, well, I'll just call this one sec-butyl cyclohexane. But that's actually not correct. There's no need to put a locant here. This is what we call redundant. There's no need to put that there because there's only one substituent. If there was more than one substituent, you'd have to put a number there, but there's only one, so we just get rid of that. And the answer is sec-butyl cyclohexane would be the name for that molecule. If you're wondering about the complex naming system, again, I'm not really all that stressed about it, but the way that you would name this substituent as a complex substituent is you have the longest chain, which is 1, 2, 3. So this is some kind of propyl. And there's a methyl group on carbon number 1. So this would be a 1 methyl propyl. And then you would just call it 1 methyl propyl cyclohexane. So cyclohexane. All right, has anybody been gandering at the next one? The next problem? If there's see if they could find the longest carbon chain in the next one. Anybody could tell me how many carbons are in the longest chain or the parent chain in the next one? Yes, excellent, excellent. Yes, Nicole, Zoe, you're both correct. Okay, both of you are 100% correct. We see the longest carbon chain. Beautiful. There's 1, 2, 3, 4, 5, 6, 7, 8 carbons in it. Great. Right, how did you find that? By trial and error. And that's literally how you have to do it. You have to keep trying until you find it. So now that we found that, we see that we have a methyl group here. Let me just write down the names. We have a methyl group here. We have another methyl group here. We have an ethyl group here. And we have a cyclohexyl group here. So we're going to number it in such a way to give the first substituent the lowest possible number. So if I circled this carbon in red and I circled this carbon in green, should I start numbering from the green carbon or the red carbon? So I'm going to start from the green carbon. If I started from the red carbon, then I'd have 1, 2, 3. My first substituent would be at carbon 3, but I want to give the first substituent the lowest possible number. If I start numbering at the green carbon, I have 1, 2, and my first substituent is at carbon 2. So that would be the correct way. So I'm going to erase these, and we're going to number the whole thing. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So this is some kind of octane. So this is an octane molecule. Octane. What do we got here? We've got a 5,6 dimethyl. We've got a 4-ethyl. And we have a 2-cyclohexyl. So how do we alphabetize? We've got M for the dimethyl, E for the ethyl, and C for the cyclo, right? Because we don't ignore the prefix cyclo. So now we put that all together, and we have C, E, and M. So let's write this down. So we've got 2-cyclohexyl, 4-ethyl, 5,6 dimethyl octane. There you have it, my friends. You know what's cool about nomenclature, I think, and you might not agree with me, but whatever, it's all good. It's the land of the free. What I think is cool about nomenclature is, you look at a problem like this that just looks so complex, but then you can break it down. You really break it, and you have to. You break it down into the simplest possible bits. Find the parent, look at the substituents, list, provide a locant, the numbering. Then you write down a list of what you have. You put the parent last. You write down the substituents in alphabetical order, separate numbers and letters with hyphens, separate numbers and numbers with commas, and you're done, man. That's it. That's the whole thing. Give me a thumbs up if you follow me on Nomenclature. If you have a question, again, never hesitate to stop me and ask me a question. It doesn't offend me one bit. Okay. So what I'm going to do for the next section is, just in the interest of time, I'm going to go over it a little quicker. And you're probably thinking, Mr. Dion, the class is already fast enough, man. Okay, I know the class seems like it's quick, but organic chemistry does move along at a pretty good clip. But I just want to go over naming bicyclic compounds with you kind of quickly. And the reason why is I've taught it enough to know that it's one of those things where students kind of have to master a bit of, non-bicyclic nomenclature before they tackle this. I'll kind of show you what the rules are, and then you'll have to try and work out some of the practice on your own time. But let me just show you quickly here. A bicyclic compound is when you have two rings that are fused together. So if you look at this molecule, you're like, what the heck is this crinkle in here? Well, actually, we have a 5-membered ring, and then we also have a 6-membered ring, right? You have two rings, and if you were to flip that thing on its side, it would kind of look like this, where now it's a little bit easier to see the 6-membered ring, 1, 2, 3, 4, 5, 6. But then you also have a 5-membered ring, 1, 2, 3, 4, 5. Okay, so it's kind of like two rings stuck together. And when we name a bicyclic compound, we always have bicyclic in front of the parent name. So what we do is we count up the total number of carbons in the molecule. Could anybody tell me, and this is not a trick question, how many total carbons are in this molecule? Probably figured it out faster than I did. How many total carbons are there in here? In the molecule, in the individual molecule, how many carbons are in here? 7, right? There's 7 carbons. There's the 6 that I have numbered, and then there's a 7, right? Same thing applies here. We have 1, 2, 3, 4, 5, 6, 7. So there's 7 carbons in this molecule. Therefore, I would call this a bicyclo. Bicyclo. Are you ready for this? Bicyclo. There we go. Then what you do is you make an open square bracket and a closed square bracket, and then you write the name of the parent. So bicycloheptane, because there's 7 carbons, right? Heptane means 7 carbons. Okay, so in the brackets, you're going to write 3 numbers. 3 numbers always. What you do is you look at what are called the bridgehead carbons. You see where the ring is tacked onto the other ring? These carbons here, these are called bridgehead carbons. Bridgehead carbons. Okay, so we look at the bridgehead carbon. So this is a bridgehead. Everything that I have highlighted in yellow is a bridgehead carbon. So then you look at the bridges that are attached to the bridgeheads. Okay, so that means that this would be considered a bridge. This would be considered a bridge between the 2 yellow carbons. And then this is also a bridge. How many carbons are in the blue oval? There are 2 carbons here. How many carbons are in the green oval? There's 2 carbons in that bridge. And how many carbons are in the red oval? There's 1 carbon in here. So those represent the number of carbons in the 3 bridges. So what you do is you put those numbers going from highest to lowest inside the square brackets. So we're going to write 2 dot 2. I mean, you could have put the green or the blue first, doesn't matter. And then you put the shortest bridge last. So that means that the name of this molecule is bicyclo, bicyclo 2,2,1 heptane. Okay, so that's how you name it. I have a more complex example here, and I have the rules listed on the left-hand side. It says to number the bicyclo parent chain, start at a bridgehead carbon and number the longest chain first. Now, in this example, you have 2 chains, this one and this one, that are the same length. But if you have 3 bridges, and when I said chain, I meant bridges. When you have bridges that are different lengths, you always start with the longest one first. So let's take a look at this compound. You see that this is a bridgehead carbon and this is a bridgehead carbon. We look at the size of the bridges. This bridge has 1, 2, 3 carbons in it. So there's 3 carbons in this bridge. If we look at this bridge, it's got 2 carbons in it. And then this bridge here has only 1 carbon in it. Don't worry about the methyl group yet. We'll get there in a second. Now the total number of carbons in here is 8. So that means that this compound is a bicyclo 3, 2, 1 octane. And you have one substituent at carbon 8, so that means that this is an 8-methyl bicyclo 3, 2, 1 octane is how you would name that compound. Now, there's another thing that I haven't answered yet. It says you number the longest carbon chain connectors first. So I'm going to erase all of this, okay, and go over another rule that I haven't really covered yet. You always start at a bridgehead carbon when you're numbering. So that means you could have put number 1 here, number 1 here, it doesn't really matter. But you always start numbering through the longest bridge, then you go to the next longest, and you end up on the shortest bridge. So we're going to start here, then you go through the longest bridge, which has 1, 2, 3 carbons in it. You go to the next bridgehead, then you go to the second longest bridge, which has 1, 2 carbons in it. Then after that's done, you go to the shortest bridge, which has only 1 carbon in it. And that's how we get those numbers, 1, 2, 3, 4, 5, 6, 7, 8. If you have a bridge with 2 carbons or more, and it's got a substituent on it, you number it in such a way to give that substituent the lowest possible number. If we look at these two here, on the one on the left, we're starting on a bridgehead. Carbon number 1, 2, 3, 4, 5, 6, 7, 8. Nothing wrong with that. And you see that we end up with a 6-methyl. However, if you started on this bridgehead, you'd follow 1, 2, 3, 4, 5, 6, 7, and then you go up to just number the last one. Now you've got 7-methyl. 7 is higher than 6, and so this is incorrect. Could anybody provide a name for this compound? I'll give you a second to think about it. So this is some kind of 6-methyl bicyclo something. And I know it would take a long time to type it, so I'll give you a second. Okay, I see that Luke's got a name. And Luke, I like it. I think it's really good. He's got a 6-methyl. And then he's got bicyclo, open bracket, close bracket. There's a total of 8 carbons in the bicyclic system, so it's some kind of bicyclooctane. And then he looked at the sizes of the bridges. This bridge has 3 carbons in it. This bridge has 2 carbons in it. And this last bridge only has 1 carbon in it. And there you have it, man. So 6-methyl bicyclo 3,2,1 octane. That's it. That's how you name a bicyclic compound. With all that in mind, let's try and name this bicyclic compound. Now this one's kind of weird because it doesn't have a bridge going over, there isn't a 3rd bridge, is there? Let me help you out with this one. Here are our bridgehead carbons, the one in green, the one in yellow and the one in green. Could anybody tell me my longest bridge, you can see my longest bridge has 4 carbons. That's pretty obvious, I think. So 4 carbons. Would I start numbering from the carbon in green or the carbon in yellow? Based on all the rules. Yes, absolutely, Zoe. You'd start numbering at the carbon in green, wouldn't you? The reason why she said that is because if you start on the carbon in green, you have 1, 2, 3, 4, 5. You have a 2,2 dimethyl, or it's actually a 2,2,5,7 tetramethyl, but either way. If you had started on the carbon in yellow, you'd have 1, 2, 3, 4, 5. So the way that we have in red, you've got 2, 2, 5, but the way in blue, you've got 2, 5, 5. So this would be your tiebreaker. So the way that we have it numbered in red is correct, and the way in blue is incorrect. So I'm going to erase all that. So we've numbered the longest carbon bridge. So 1, 2, 3, 4, 5, 6. We go to the second longest bridge, which has 7 and 8. And then there is no bridge here, is there? So the last bridge has 0 carbons in it. If we look at the whole bicyclic system, this is some kind of bicyclo. We've got 4 carbons in this bridge. We've got 2 carbons in this bridge. And then we have no carbons in the bridge here. So that gives us a 0 as our last number. So 0. So bicyclooctane, like that. And now we're just going to list all the substituents. We've got methyl groups, 2 at carbon 2, 1 at carbon 5, and 1 at carbon 7. So we've got, I didn't really give myself enough room here, did I? We've got, see if I can squeeze it all in here. 2, 2, 5, 7, tetramethyl. There you go. 2257 tetramethyl bicyclo 420 octane. Nothing to it. Okay, I think we're going to take a short break and then we're going to come back and we're going to talk about constitutional isomers. Compounds that have the same molecular formula, however, have different connectivity of atoms.